general compute nodes on a system here at Nix called Daughter. And the goal of this slide is to show you that there are many events you can measure for example, on this particular system that uses Intel machine processors. So the library has three different parts: functions that you can use when profiling the code, and there are some also low-level functions that help you to access, like very specific information if you want. And of course, there are a bunch of PHP utilities that will make your life easier. How the functions look like? Well, okay, there is a version for C and there is a version for Fortran. So here you can see, how the interface for each of the functions look like. All of the functions in C will start with the uppercase PAPI underscore and then the name of the function. And then in Fortran, they will all the function names will start with PAPI F and then the name of the function. And whenever you're programming with C language, you need to include the PAPI.h header file, and then when you're working with Fortran, there is a header file as well for Fortran called fPAPI.h. Here's a list of high-level functions that you can use. So on the left you can see the name of the functions, and on the right you can see a description of them. The arrow list, they all do something different, and you might not need to use all of them. You might want to use a few of them. In the example section, I'm going to show you what you can use. Here are subset of the low-level functions available through the API. There are many low-level functions available. I'm just showing you a small subset. But anyway, just to show you how it looks like. And here are the API utilities functions that they can actually be very handy. So, for example, if you want to measure the time, API offers you probably the best way to measure time. If you want to time functions or your program, of course, the standard library of C has, like the time function. But if you ask people, they will tell you that it's not as good or as great or as precise compared to the PAPI functions that will actually, get the very, very low-level information in order to get really accurate information. To get very accurate timing on your function. So an example. This is an example code that shows how to multiply two matrices. There is, this is a very simple program, and I want you to see that, for example, on the top, there is the header file for C that needs to be there for this C code. And then in the middle, you can see the code for it's a triple inner loop where the actual matrix multiplication happens. But around it, before I go, you can see that I have the function called for PAPI flops. PAPI flops is a high-level function of PAPI that will probably do most of the things that I will want to do when I'm, instrumenting my code, and then I want to see, what the performance of my code is. So the philosophy of this is when I want to instrument a particular section of my code, if I call PAPI flops, then PAPI flops will access what information is required or needed, saving those, the variables used as argument for the function. Then I work, and the registers, the performance count, the registers are going to count, whatever information needed or what's requested for that function. And then when I'm done, I call again the PAPI flops, which is going to read, with the new information and then subtract, and then finally all information about what happened during the execution of this section of code, or basically between each call of the PAPI flops. All the statistics are already in the variables that are used as parameters, and then I can print the results to my screen. You compile the program with PAPI, well, on the right you can see on another cluster, well, you might need to specify the location of the header file. You might need to specify the location of the live of the PAPI library. On a query system, I'm going to show you, give you an example on the query system. Well, you don't do that. It's actually simpler. You will just need to load the PAPI module and then just compile it. And somehow the software environment is going to take care of the details of what the PAPI library is. So just that, just a long version of Darter. I think I won't have time to do the live demo of this, but here you can see all the steps needed in order to do my program. For convenience, I swapped from the Cray compiler to the GNU compiler. I had to load my code, and then I compiled, and then when I run, I got my statistics on the bottom. One little caveat is that this is an example. I'm using an example that is publicly available on the internet, and you can see the link on the top. But it happens that this code doesn't compile directly. Why? Because it's going to throw an error message that the PAPI underscore P error is getting the wrong number of parameters. So here I have a small one line to fix source code, get rid of that error. Here's another example where you can see, if you want to use native events, well, there are other function codes there available that you can use to do this. And here you can see that what will be the code of which you always need to call the PAPI library init in order to initialize the library. In this example, I didn't have to call PAPI init because the PAPI flop will take care of that. But still, at the end, I do a PAPI shutdown just to clear things out. Anyway, as a reference, well, the best reference information you can get from about PAPI can be accessed from the website of the developer. So you can use Google to type PAPI, or just go to the icl.cs/PAPI, and the manual guides, source code is available. I'm done, and I think I will move to Pranesh. Waiting for Pranesh. Yeah. Mm-hmm. Well, I suppose you have any questions, you can put it in the chat, and I'll be PAPI mention your code, can you slow it down at all, or is it too? Yes. Yeah. Yeah, the performance answer that not actually used. Supposed to be okay. But I think if you ask them, they will not tell you that it's extremely good. I think. Doesn't mean that. In terms of ethics, well, the outcome, yeah. Well, okay. What I know is that you can be a little bit tricky to use like failed functions from the API that kind of like summarize, low level functions. Sometimes uh, the preset, the API preset, not as accurate because it will be and then maybe they have tried those presets for some of their architecture, and then when you move to a different architecture, well, maybe those presets, genetic presets, they don't work as well because the way they were coded, the presets become the native event, and then somebody has to hard code, how which native event I'm going to be using to actually give you the information for the API preset, and do it right, you will get you can actually, and of course then from one generation of a processor to the next generation of a processor, things can change. And so if you are using the native event, you should, the information should be accurate. So if you're using a high level genetic event, yeah, how, yeah, you can get it wrong. Okay. I don't think that has an angle. She's a for the other application. So if you're going to use the microphone on the computer, you need to the little screen to begin to make sure that you select computer audio if you're using telephone well. Otherwise, audio. Hello? Yes. Did you, when you start the WebEx connection, there is more screen, pop-up screen that shows to do how to do the audio. There is a here I can see on the meeting that you don't have audio in the somehow like maybe you didn't click OK on that pop-up window. Okay. Mm-hmm. Mm-hmm. The couple of windows. Well, the you want to use the audio via computer or via telephone. Yeah, that's what I was gonna say. I can see that you were in the list of candidates. So somehow, yeah, I still see you on the list. No, make sure you still. Oh, you did. Oh, I think she can see you. How you? So you're connected. Actually on phone computer, yeah, you should be able to hear you. Let me try on the audio on the computer. Can you take it? Okay. Yeah. Okay, come back. Okay, yeah, you come back. Yeah. You just came back. So, like, you're choosing the person. So, maybe the speaker. The window that says audio. See the window that asks how. One on or computer phone or phone that phone or the phone or use the computer. Well, okay. Uh,
Yes,
okay, I can hear you.
can you my presentation? It,
Yeah, I can hear you.
presentation, huh?
Yeah, I can hear you.
How about presentation slide? Can you see
Yes,
it?
yes. Everything is fine.
Okay, sorry for this trouble. So today I'm going to talk. So about the profiling tool and the outline of my talk. First, I'm going to about profiling, what does it mean, and why we should worry about profiling, and how much topic Daniel has covered about the basic profiling, but I saw his presentation about PAPI. So I'm going to talk about PAPI in my presentation, but I will cover FMCI and CREPAT. At the end video, I will introduce some profiles on this. So start with the introduction. There are six performance available on Kraken, like CREPAT, PAPI, FPMPI, Kelaska, IPM. Tools has different levels of functionality and complexity. And I want to go through all those tools. It may take few days to go through all those and present information about each and every tool. So that's why for my today's talk, I'm only going to talk about FPMPI and CREPAT. So here is the typical development life cycle of code, like what it means to develop the code. So basically, first of all, you have the algorithm, and algorithms you write the code in your language, maybe C++, Fortran, or Python. And then if it's a compiler language, then you compile the code, it executes the binary, and it may possible you face some segmentation fault issue or some type of memory issue, then you need to debug your code and enter the steps comes in, which is tuning. And so that's why we are going to talk about and tooling tools today, because it's important in HPC environment. That way you can improve the performance of your code, you can see the bottleneck in code, and you can, if you get it out how to correct those, then you can run your code much faster. So what unique performance issue? How do you say that my code has some performance issue? So my code takes 3 hours to run. Does mean it's perform poorly? I think it depends, because even high performance research benchmark on certain cores, it can take couple of hours, because it does a lot of floating point operation, and it's to get maximum out of the machine. Another thing is you need to consider single core performance problem, and once you solve the single core performance problem where you improve the code and get some more performance out of it, you may think about how you can make it parallel. And to make the parallel, the other things comes in, which is scalability. And to measure all this performance, like where is my bottleneck, it is helpful to have the profiling tool. So here is the high performance issue. So is fraction of the peak. So when if you get the 20% of peak, which is usually decent, once you optimize your code, and after that, if you decide you still want to improve the performance, then it's up to you. Work that code and performance. As I mentioned before, scalability. And there are two different categories in the scalability. One is strong scalability, where you don't improve the you don't increase the problem size, but you throw more processors to it, so you can solve the problem in this. So the runtime increases by twice x when size of course, then it sometimes it's symptoms of strong scalability, and remains the same when I the amount of work per core same. That is the weak scalability. for generally most of the people, when they want to figure out the performance issue, they start with putting the time function into their code and see how much time it takes to finish this particular function or routine. Two different ways you can do. One is called include time, where you the time of whole routine or function, and the exclusive time where you exclude the time calling the other function from that function. So I see here foo, which is in function, and we can get the time of foo function, how much time it takes overall. But there are first foo1 and foo2. So also get the time for foo1 and foo2. So x means you subtract the 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 time foo2 from time foo, and then you get the exclusive time for foo. So how to profile? So the first you can do is like just put the time of functionality into it, and another you can do is you can compare your previous run with the current run, and based on the input parameters, you can say, oh, this parameter, this per data set takes less time than this one. But in a way, you cannot pin the performance bench bottlenecks. So what other options we have is you can include copy function call into your code, and then you can get more information about the performance of your code in terms of how much time it spent calling the in terms of counters and cache miss and the TLB misses. And the other option, which is more functional, calling copy function within the code, is performance tools like Graypat or PMPI or IPM, where you just manually recompile your code and run it again and get this text file or some type of file format which that tool can understand and visualize it. You have the code, and so what for the sequential code, where it could be the performance bottleneck. In the figure, you see the typical computer where there is a CPU and 3 level of caches, and there is a main memory. And do it like where am I spending time? Am I spending time in calling some libraries or functions or some statements? Or is there computational intensive kernel in your code? And match my intentions, because you know, like, oh, this function should take more time. So that place is where you can look for in your sequential code for the performance improvement. And impact hierarchy is also big for the performance. You need to think to figure it out, like, do I have excessive cache misses, or how data locality works, because if you have multi-threaded program, then data locality is really important. If data is not a particular thread, then you have to pay cost to accessing the data from the socket or from external resources. Like, is my IO efficient, or how much time I spend in system libraries. The where what are the for improved for shared memory architecture. So here, like, two CPU are sharing the main memory. So single storage, and the RAM can be accessible from any CPUs. Common programming models are PEAT and OpenMP, and the typical performance issue in this kind of environments are false cache sharing, where multiple processes are updating the cache, and that's why you have to to read, you need to access the data many times from the cache. Organization, that means multiple processes are synchronized on main memory, and you have to pay the cost for that as well. The reading overhead is also the important issue for shared machine. The NUMA, which is non-uniform memory access, where multiple data connected, multiple processes are connected to the shared memory machine. And here the important thing to keep in mind is you have to have the first test policy. So whenever you start it, you have to get the memory for those, so that way thread with the better quality to access that data. And I talk about the serial version of the shared memory architecture kind of code. Now let's go to the message passing. So message mostly used in the distributed memory machine or model. This kind of architecture where multiple nodes are connected through the spatial interconnect. And in here you use mostly the MPI library to communicate with the node. And the important factors here to keep in mind, one is like low message rates or network bandwidth or operations. So if you have MPI code and you use some profiling tool, let's say Graphic, then it will print out the information about how much time it spends in the communication, how much spends for MPI send and the receive, how much data it transfers between the nodes, and they can get the idea where you should improve the code. So the important thing is, what data should I collect? So the MPI statistics, where how times you call the MPI routines and how much data you transfer. Another thing is IO statistics, how much time spent in reading the data and writing the data to the disk. And processors are performing the IO operations. And the hardware performance counters are also important, as describes the PAPI is the library to get the information about hardware performance counters. And they have this terminology for static sampling and event tracing. And here is the what are the data types for that. So in profiling, generally get the report for statistical distributions across all reported locations. That means all reported nodes. You get the call tree and the OR graph, which function call which function. So you get this whole hierarchy of the functions. The inclusive timing as well as exclusive timing, and profiler tools, they also give hardware counters. There is the thing is also important, which gives you the log of MPI events, and it also gives you the log of timestamp events. And the list of some tools which are able to do the profiling. Start with the basic ones. So in system, as I mentioned, there is this time utility. So you can time how much time your program takes or how much time this particular function takes to run. It is utility and stress. It gives you trace of your function calls and also the dependent libraries. The PAPI is really popular. It's from UPK, and there is another one from Los Alamos National Lab, which is called PIPER. From University of Oregon, it's a comprehensive framework. It provides all different kinds of statistics and performance analysis reports. Also has the 3D visualization capability, so you can visualize your results in the viewer. And like HPC toolkits from University, which provides you the call stack analysis and the IPM, SCADA. The vendor which I'm going to talk right today is Craypad. It also has one which is called HPC Toolkit. MPI tools, which specifically targets the MPI code. Is very really popular one in HP community. The IP code developed at Lawrence Livermore and Operational Lab, and AI from Aragon National Lab. And to do the visualization of this report, JUMP is the visualization tool for analysis reports. So the PAPI, as Daniel described, it's already installed on Kraken. You just need to load the module, and you can use PAPI tool. Setting the ground for the FPI, because you can integrate the FPI and PAPI, so that way you get the performance counter results while you are using the FPMPI. So let's talk about specify the hardware counters in your scripts. So you are using the FPMPI or IPM, which is the interactive performance monitoring tool, or TAO is the utilities. So you need to use the environmental variables like PAPI _ flops if you are interested in getting the flops information. There are also, for the CRET, there are these two key hardware counters, and you can use the environmental variable called pat _RT _ hardware HPC, and you can specify the number, and then use that particular count group's information. So so FPI, what it does, it intercepts the MPI library calls via MPI profiling interface, and use the report for CPU times, stack, as memory uses, and also like how much depend on each different MPI functions like MPI send, receive, wait, and so on. So easy to use profile library. You just need to link your code with FPMPI. So on Crack we have FPMPI _PAPI module. So it provides you the MP related information as well as the counter information. Another thing is there is always an overhead to the profiling tools. So FPMI is the rank 0 to write all the data, all profiling outputs. As far as I know, this one is the lightweight MPI tool to MPIP, so it doesn't have much overhead. So here FPMPI provides, and then we can go the report which I generated for FPMPI on Kraken. So as the CPU time, memory uses, MPI call statistics, and performance counter. To FPMPI on Kraken, you need to module load FPMPI _ PAPI. You link your code with FPMPI _ LDFlex, and it's good. And then after FPMPI will intercept MPI code. To PAPI, you need variable MP _HWPC counters equal to PAPI filtrations, that is PAPI _FP _ops. You submit the job, and once you will get the profile.txt file. So here the output of FPMPI is ran on the 16 processors. So it gives the process states, minimum time take the MPI rank, maximum time taken by MPI rank, average time, whether it's balanced or not. So if if the 100%, that means it really balance functions or the routine. And it says rank, so that means rank number 59 to minimum time is 27.93 seconds, and rank 0 to 28.03 seconds, which is the maximum time. So list you this IO time, IO write time, communication time, synchronization time, and it also gives you information about memory, like how much data, how memory it used. Use in the previous slide, we said the PAPI flop of underscore FP underscore ops variable. So here it gives you the information about the flops, and it gives you the information about MPI, how much time each MPI function took, like M barriers, the number of calls, and the completion time. And like I already used MPI broadcast, MPI send, and so on. So just there's questions about FPMPI so far. Okay. So yeah, so the FPMPI is it's a real lightweight tool to get basic information about your MPI functionality and how much time it takes. What I mentioned is the load imbalance factor. You see in this slide, it's a second column. It says IMBL. So basically, it's a factor calculated for each item reported. This value can indicate the cases where one case is doing more work than others. And it limits the scalability. And a job to report 0% load imbalance. So as you, some of them are 0%, but some of them are like 18%. And if you here, then it's like for the MPI communication, it's 32%. So that code really well. So let's. So Daniel.
Yeah.
Just know how much time we have.
That's fine.
Okay, thanks. So a performance analysis framework consists two things. One is called CRAPAT. Another thing is CRAPApprentice. So CRAP is the CRAP performance analysis tool, and CRAP provides you the nice graphical to visualize the data generated through the CRAPAT. This the important one is called pat_build, which provides the automatic instrumentation. Time library, but it's transparent to the user, so we don't need to worry about that. And that_report, which gives you the performance analysis report. Build does the automatic instrumentation. It puts some trace into your code. It can get the information about profiling. And Pat help with. So how you use CRAPAT on Kraken? To use Kraken, you load XCRAPAT module, and you load the apprentice. So once we have the data, we can visualize it. Merge XCRAPAT and apprentice. So you just need to load one module, which is called module load tools, and should give you the capability of using CRAPAT as well as apprentice. First thing you need to do is you need to rebuild your application. So you then and you do the make again. And after we need to put some traces into your code. So you you call it build dash O, and it's the APA, that's the automatic profiling analysis, and give executable file name. In this case, it's a.out. And once that, what I'm going to here, I am interested in hardware counters. So that says pat underscore RT underscore HWPC, and my code uses MPI. So I'm interested in MPI function, MPI information. So interested in to get the information about IO statistics. My code also uses BLAST. So
Alert from calendar. Meet George at 3:30.
Sorry. So here, and then I say a.out. And once you do that, you should get a.out plus pat file. And then after, you need to run this a.out plus pat file on the compute node. So you need to change your job script and a.out plus pat. You need to run command from Lustre and then in the program. It will generate the S data files with the extension of XF. If it's multiple files, then it should be in S data directory. After, you need to do the report. You need to read the report. So pat underscore report dash O, and you give the XF file name or your directory names, and it's the report for you. And the report file as well as automatic profile analysis file, which will be some file with the extension of APA. Once you have this APA file, you can do two things. One, you can do one can visualize it, or you make sure all the instrumentation details are what you want, and then you build that. And if you want to change it, then you can change that APA file, and then you do the build again with the pat build dash O a.apa, which will give out as APA file. You run this file again on the compute node and give you the report file with changes you made with in the instrumentation file. The apprentice can visualize this data. How the visualization look like. So here is just the report, just a text file, but in the later slide I will show you the visualization as well. So in the pat report, which gives you the timing information, calls, and the groups. So here the 39% of the time it's spent in the BLAST function, and it also gives you which BLAST function. So like I'm DGM, DRSM, DCopy, DGMV, and it's similar for MPI, IO, MS library, and so on. And as you remember, I specified pat hardware counters. So it means the PAPI flops information as well as hardware flops information, which are in rates. So it gives you the so the tool. Here is the bar. It has all kind of functionality like inventory report, activity reports. It can give you the call graph. It can give you the mosaic reports for communicatrix. It can give you the hardware counter information as well as IO information. Default, it looks like something like this. When you feed in the report file to the apprentice, it says how much time it spent in API send, receive, by default it's sorted by calls. You can sort by time, and so on. And the call graph, how call graph looks. So the main function, then it calls the HPL function, which is slide and type performance linear benchmark. So linear benchmark. So it's showing the HPL main, HPL placed and functions. And here is the last thing, which is the mosaic report. So Afferent is, it has this functionality for the mosaic reports for the communication metrics. So here communication metrics, source, destination, and how much time to do the communication between the nodes. So the GrayPad, it's a really good tool. It gives you a lot of information about MPI communications, MPI function calls, and other libraries like BLAST, LAPACK, ADHDF5, NucleF, MKL, and so on. So it is kind of like modern performance analysis. So you don't need to change your code. You just compile your code, and it can give you all this information. So it is good to analyze the performance data from the single one. But with the fact, if you are running the code multiple times, then the thing is sometimes become difficult, because then you need to keep track of all different runs, and compare. Those kind of facilities are not still in the GrayPad. But for simple analysis, performance analysis, GrayPad is really helpful tool. Here are some of the resources which I talk about, like FTI, Tau, MPIP, IPM, and Skillasta. So that and Daniel.
We're good. Thank you very much.
Okay, thank you.
Thank you.